All right, we are back and we are ready to go. Let's see what we have here. What is the expected value of x? Well, easiest way to do this is to use the table to fill in the marginals probabilities. So adding up that first column is going to give us 0.10 here. Adding up the second column, 0.35. Adding up the third column, 0.1, 0.35, 0.1. That is 0.55. So the expected value of x then, x takes on a value 1 with probability, 0.10. X takes on a value 2 with probability, 0.35. And x takes on a value 3 with probability, 0.55. And running that through a calculator there, let's see, what do we get here? I've got 2.45. All right, looks good. Expected value of y, same thing. Let's get the marginal distribution from the table by summing across the rows. 0.05, 0.05, and 0.1. That is 0.20. Second row, adding that together, that should be 0.50, and then 0 plus 0.2 plus 0.1 is 0.30. As always, a quick check, your marginals, when you sum up that final row or final column, those should total to 1, and indeed they do in both of these cases. Just a quick check to make sure we didn't make an arithmetic mistake. What's the expected value of y then? Takes on probability, takes on 1 with probability 0.2, takes on the value 2 with probability 0.5, and it takes on the value 3 with probability 0.3. And so running through that computation, I've got 2.1 as the expected value for y. And so the last thing we need before we punch in our formula here for the covariance is that we need the expected value of x times y. And so let's go ahead and work through that. So I'm going to go through each pair of x and y. So I go through that. So let's see here. We're going to go, I'm just going to go from down each column, I think. So 1, 1. And it doesn't look like there's that many 0 probabilities except right here. So I'm actually going to need most of these probabilities. So it takes on the value 1, 1 with a probability of 0.05. Let's do when x is 2, y is 1. That is probability 0.05. And when x is 3 and y is 1, the probability there is 0.10. Second row here, that is 1, 2. 1 times 2 times 0.05. 2 times 2. X and 2 and y is 2 with probability 0.10. X is 3 and y is 2 with probability 0.35. And then I don't need the 1, 3 probability because that's 0. But 2, x is 2, y is 3. That has probability 0.2. And x is 3 and y is 3 with probability 0.1. And so we run all of those through a calculator here. I have 5.15. Check my work, see if you agree. Did you get 5.15 when you did this? When you paused the video? Hopefully you did. So once we have these numbers, then the actual computation of the variance is really not too bad, right? So the covariance, expected value of x times y minus the expected value of x times the expected value of y. So then with all this, then the covariance of x and y is equal to 5.15 minus 2.45 times 2.1, and that is equal to 0.005. 0.005. Good. So what do we have here? In terms of a sort of practical standpoint, right? What does this mean? What's the intuition here behind saying covariance is 0.005, right? It's positive. It's a small number, but don't dwell too much on the size of this number here, okay? So I want to note that the 0.005 being small This does not mean it's a weak relationship. Does not mean it's a weak relationship. It's a positive relationship, and that's all it tells us. There's a positive covariance. So if x goes up, we expect y to go up as well. It does not mean that it is a weak relationship. Covariance does not measure the magnitude or strength of the relationship, but rather just the nature of it. Let's write that down. Does not measure the magnitude or strength of the relationship. Just the nature of it. That's positive or negative. Just the nature of it, okay? Why does this not measure the magnitude or strength of the relationship? That is because covariance is not scale-free. It is not scale-free, right? The size of the covariance depends on the units. Depends on the units being used in your problem with your random variables, okay? For example, if x is 1, 2, and 3, and y is 1, 2, and 3, those are relatively small units. If I do this same question, but I say x is 1,000, 2,000, and 3,000, and y is 1,000, 2,000, or 3,000, then I'm just gonna, I don't change the it's not changing the relationship, it's just changing the units, if you will, right? The probability distribution would be exactly the same as this table, but that would drastically increase the expected values, and it would drastically increase the covariance. It doesn't mean a stronger relationship, right? It depends on the scales, or the scale that you use, the units that you have. It depends on the units that you have. So what if we want to know something that's not just the relationship, whether it's positive or negative, but we want to measure the strength? Is there a scale-free measurement? And sure, that is called the correlation coefficient. Correlation coefficient. The correlation coefficient is scale-free. It is scale-free. It is scale-free. So let's go ahead and define the correlation coefficient. This is definition 4.5 in our e-text. We have rho of xy. That is the Greek letter rho, R-H-O. I don't know if we've seen that yet here in this class. Rho of xy is equal to the covariance of x and y divided by the standard deviation of x times the standard deviation of y. Or, depending on the notation, it is the covariance of x with y divided by the square root of the variance of x times the variance of y. The square root of those variances then would be the standard deviations, naturally, right? Okay, so what can we say about the correlation coefficient? When you're dividing by the standard deviations, you're actually you're standardizing your covariance in some sense, and it's got a couple of nice properties. One of them is that the covariance then is bounded on both sides by plus and minus 1, right? Rho of xy, the correlation coefficient, is bounded between plus and minus 1. So the sign of it would indicate whether or not it's a positive or negative relationship, and the closer it is to 1 or negative 1, the stronger the relationship is. Then you could start comparing different correlation coefficients, and that's an apples-to-apples comparison. You cannot compare covariances between several pairs of random variables unless the scale is the same. But you can always compare the correlation coefficient. That is just a true unit-free measurement. I'll also mention that if the correlation coefficient is exactly equal to plus or minus 1, then there is an exact linear relationship between x and y. An exact linear relationship between x and y. What I mean by that is y then is equal to some function of x, some linear function of x. Y is equal to ax plus b if your correlation coefficient is equal to 1, right? Okay, that's what that is. So that's kind of interesting. So we have a correlation coefficient. Let's just punch out the correlation coefficient for the last example. We already have the covariance as 0.005. In order to get the correlation, we would need to divide by the relevant standard deviations, right? So continued here, continued. We have sigma xy, the covariance is 0.005. We need then sigma x, the standard deviation of x, and sigma y. Okay, so let's go ahead and work through that. How do we get sigma x? The standard deviation, remember, that's just the square root of the variance. So in order to find the variance, we need, remember that the variance of x is equal to the expected value of x squared minus the expected value of x quantity squared, right? So we know the expected value of x is 2.45. What do we need then is we need the expected value of x squared. So we need expected value of x squared. All right, so what is the expected value of x squared equal to? Expected value of x squared then is equal to, let's see here. Remember, x can take on the values 1, 2, and 3. 1, 2, but this should be x squared. So 1 squared, 2 squared, and 3 squared. And what is the probabilities it takes on those values? I gotta go back to my table here. X takes on the value 1 with probability 0.10. And then 2 is 0.35, and 3 is 0.55. 0.10, 0.35, and then 0.55 for 3, or 3 squared in this case. And so we run that computation there. We should get 6.45, which is the expected value of x squared. So the variance of x then is 6.45 minus the expected value of x quantity squared. What's the expected value of x? That was 2.45. 2.45. There we go. And so I've got that to be 0.4475. There we go. That's the variance. We also need the expected value of y squared to get the variance of y. So variance of y, we need the expected value of y squared, whatever that is, minus the expected value of y quantity squared. So what's the expected value of y? Expected value of y is 2.1. 2.1. So that's 2.1 right there. What's the expected value of y squared? Remember, y can take on the values 1, 2, and 3 as well. So I've got 1 squared. The probability that y takes on the value 1 is what here? 0.20. 0.20. And then it's 0.5 and 0.3 for the other ones. So 0.20 plus 2 squared times 0.5 plus 3 squared times 0.3. And so what is the expected value of y squared? Running that through a calculator, I've got 4.9. So that goes here, 4.9. That will give me a variance of y. And the variance of y then is 0.49. 0.49. Okay, cool. So then, Rho, the correlation coefficient, is sigma xy over the standard deviation of x times the standard deviation of y. So what is the covariance? 0.005 divided by, now the standard deviation, and that just is the square root of each of these. So that's the square root of 0.4475 times the square root of 0.49. Okay? Which the product of a square root is the same thing as the square root of the product. So, or in the denominator, you can just have the square root of 0.4475 times 0.49. That may be kind of nice to do in terms of putting in a calculator. You could just do this product and then take the square root of that. Then do 0.005 divided by that answer. And I've got this approximately rounded off to 0.01068 here. 0.01068. Okay. So now with that, I could say, since the correlation coefficient is close to 0, it's a positive relationship, but it is a weak linear positive relationship. There is a weak linear positive relationship, relatively small.